Power functions with positive integer exponent, investigation 1. In this investigation, we will study the properties of functions of the form y equals x to the power of n, where n is a positive integer. So you may remember that z was the set of all integers, including negative ones, 0, and positive integers, and z plus is the set of all positive integers. So, for example, we can think of function x to the y equals x to the power of 1, x to the power of 2, x to the power of 3, etc., etc. Okay, so in part A of this investigation, we will use the GeoGebra Graphing Calculator app to draw graphs of 6 power functions, and here they are: function f sub 1, y equals x, function f sub 2, y equals x squared, and so on until the function f sub 6, y equals x to the power of 6. Or alternatively, you can use this interactive prepared beforehand by me. So you just click on this link and what you get is this interactive here. So we will work with this. Here are those functions. So on the left, you can see them written here. So f1, 2, 3, 4 until f6. Here they are distinguished between themselves by different colors. So the straight line f1 is the function y equals x. Then we have, well, this is very familiar. The graph is a line passing through the origin and also passing through the point 1, 1 and minus 1, minus 1. Now you may imagine another one. The red one is the y equals x squared, and it's a usual parabola. It's this one here, okay, and on this side it's there. Okay, then there is f equals x to the power of 3, and this is in orange, so you see it here. So it goes like this, and here in the third quadrant like that. Then there is f to the power, well, y equals x to the power of 4, which is in this color here, so it's like that. So it's similar to parabola, but well, it rises somewhat slower first and then increases very fast, and also on the left hand side, etc. Okay, so here are the functions, all of them, and you may notice that for odd powers of the exponent, those functions, so in our case, y equals x to the power of 1, y equals x to the power of 3, and y equals x to the power of 5, they are positioned, or they exist in the first and in the third quadrant. Now, if you notice just those with the even power like these, so the red one is x to the power of 2, x to the power of 4, and x to the power of 6, they reside in the first and in the second quadrant. Okay, so I will now make them all visible and go back to the exercise. So we have used this program to graph these functions, and now in part B we are asked to explain why all the graphs pass through the point 1, 1. So you may have noticed that all of those functions pass through this point with coordinates 1 and 1. Okay, so why? Why is that? So let us think about this for a while. Imagine a function y equals x to the power of n. So it's a function, in general, let me call it f. Okay, so what would be f of 1? So the function value at x equals 1. Well, it has to be 1 to the power of n, because I substitute 1 for x. Okay, so 1 to the power of n. What does it mean? 1 to the power of n means that you have to multiply 1 by itself like this, etc. And all of that should be done n times. Okay, So what do you get when you multiply 1 by itself n times? Well, of course, you must get 1. And therefore, the point with coordinates x and y, which is a point of the graph representing this situation, should have the x coordinate corresponding to the x value here, so it's 1, and the y coordinate should be the answer that we obtained, so again, it's going to be 1. This should explain the fact that all the graphs pass through the point with coordinates 1 and 1. Okay, now in part C, explain why the graphs of all power functions with an odd integer exponent pass through the point with coordinates -1, -1. Okay, so let me make visible only those which have the odd integer exponent. So here they are. And the question is to explain why all of them pass through this point with coordinates -1 and -1. Okay, to see that, let us consider again the same function here, but this time we'll try to evaluate the function value at -1. So f of -1. F of -1 should be -1 to the power of n, where n in this time is an odd number like 1, 3, 5, etc. Okay, so what happens is that you have to multiply -1 by itself, okay, like this, and you have to do it n times again, but this time the number of n is odd. And what you may have remembered already from the prior lessons in mathematics is that whenever you do that, well, there is the missing minus. Whenever you do that, your answer is going to be -1. And therefore, using the same logic as before, the point x, y with coordinates x, y, which corresponds to this, will lie on the graph where x is the number that we have used here. So x has to be -1, and the y is the function value that we obtained, so it has to be also -1. So if you wanted to graph this point, it would be there in the graph and its coordinates would be -1 and -1. So again, it explains the fact that all the odd integer exponent or odd integer power functions pass through the point with coordinates -1 and -1. Okay, in part D, explain why the graphs of all power functions with an even integer exponent pass through the point with coordinates -1 and 1. Okay, so let me make visible only those which have the the even power, like x to the power of 2, 4, and 6. And the question is to explain why all of them pass through this point with coordinates -1 and 1. Okay, to do that, we try to do the same thing again, but this time we try to evaluate the function value of x at x equals -1, but the only difference here, well, it's going to be -1 to the power of n. The only difference is that n is an even number here. So we have to multiply -1 by itself, but we have to do it even number of times. Okay, so this is an n times again, but this time it's even number, like 2 times or 4 or whatever. Okay, so there is again missing minus. So what do you get when you multiply -1 by itself, but you do it even number of times? You have to get +1. Okay, so this means that the point with coordinates x and y should be on the graph, and x in our case is -1, while y is +1. Okay, so this should explain this. The reason for that is that the properties of power function, or the properties of powers, tell us that this should be so. Okay, so the next part is part E. Explain why all the graphs pass through the point with coordinates 0 and 0. Okay, so this one is the most trivial, I think. You just, well, you see all those graphs and all of them pass through the origin of the coordinate system. So you may already know the answer, but just for sure, I'll try to show it to you. So the function value of all those functions at 0, so f of 0, should be 0 to the power of n, whatever n is, whatever positive integer you can think of. What does it mean? You have to multiply 0 by itself, and you have to do it n times. Okay, so again, n times. So what do you get when you multiply 0 by itself n times? You must get 0. So this is what comes out as a result, and therefore the point with coordinates x and y should be on the graph, and this time it's the point with coordinates, well, for x we substitute 0 because it's this one, and for y you substitute what you obtained, so it's again 0. Okay, so the point 0, 0 lies on the graph, and it must do so. Okay, now the last part of this exercise, part F, play with this dynamic interactive model. Okay, if you click on it, you should get a different model. So I will try to open it from this window, and it should be this model here. So I'll choose to edit. Okay, and I should get it here. Yeah, here it is. So this is the interactive model that we have to play with. Okay, so you should see it like this. So play with this model prepared in GeoGebra. Explain why, as the power increases, the graphs flatten near the origin and become steeper away from the origin. So first, what is the origin? The origin is this point, the origin of all graphs. So it's the point 0, 0. Now, the only thing I can do here, well, you see this is the graph of the function y equals x to the power of n. The only thing that I can do is to increase the value of the slider. And this can be done only by units of 1. So first the slider assumes the value of 1, then it's, well, I can change it again. It's 1, now it's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so what you saw is that for odd powers of n, the graph resided in the first and the third quadrant. For even powers of n, it resides in the first and second quadrant. Moreover, what you see is this behavior that as you increase n, okay, like this, the graph flattens out here in this region between 0 and 1 and becomes more steep in the region of x values greater than 1. Okay, so look at it again. I will first take this slider to the smallest value, and as I increase it, the graph becomes flattened in the region between 0 and 1 and steeper for higher values of x greater than 1. Okay, so why is that? Okay, why is such behavior present? So you may imagine, for example, there is the number of 0.6 here. Okay, so imagine now I have the function value is 0.6 to the power of 4. How do you obtain it? You take 0.6 and multiply it by itself 4 times. So every time you multiply by 0.6, the answer becomes smaller. It's 60% of the previous value. So first you start with 0.6, then 60% of that, 60% of that, and again 60% of the last answer. So therefore, as you multiply more and more times by 0.6, the answer becomes smaller. So you see, you can observe it here. If you concentrate on the function value at 0.6, you see that as I increase n, the function value decreases because it amounts to more and more multiplications by 0.6. And this is true for all values between 0 and 1. But it's different for values greater than 1. So imagine you take the point 1.2 and take the power of 1. Okay, so let me move this slider to 1, okay, like this. So at 1.2, you have the function value of 1.2 to the power of 1, which is 1.2. Now, when you take 1.2 to the power of 2, you have to multiply 1.2 times 1.2. So you have to take 120% of it. So by multiplying by 1.2, you increase this value, okay, like this. So the value at 1.2 increases to this greater value. And the more times you multiply it by 1.2, so as you increase this power to 3, 4, 5, etc., the answer becomes larger and larger and larger. And therefore, the graph becomes steeper and steeper and steeper in this region. So yeah, this should be the answer to the part F. And this should be it for this investigation.